Hello and welcome to the Bennett equation podcast. So normally I have these things enumerated. This will eventually end up in the GChem series. Probably, I don't have everything finalized, but probably in around the 60 to 70 number for that set. But this is its own separate entity because it's a very unique uh, equation that depending on what textbook you use, you may run into it, but in all likelihood, probably not. So I want to give a little history on it. In 1989, the first time I was writing a manuscript, my very first general chemistry book, I put that in there. So that's the first time it appeared in print was 1989. It since got absorbed by, at least as far as I know back then, six textbooks. I assume it's probably been absorbed by a few more since that time. So you can find it if you have an older textbook. But for whatever reason, the Henderson-Hasselbalch equation is in every book, and it's a useful equation. And you get the pH of a buffer, a mixture of a weak acid and weak base in solution. This equation is used when you don't have a mixture, just have one or the other, just the weak base or just the weak acid. And it's equally as useful, but just for whatever reason, never caught on. And I think, quite honestly, AI sort of squelched it because with AI, you don't really need the Henderson-Hasselbalch anymore. You don't really need the Bennett equation anymore. You can solve that. But I'm hell-bent on you learning it so you know what it is so that you can double-check AI, and if you use it the right way, be faster than AI. So by the end of this, that is my goal. But just to emphasize what it is, it's for determining the pH of a weak acid using just its molarity and its pKa, or it can also be used, if we wish, for the pOH of a weak base using pKb and the molarity. Okay, so it's weak acid, weak base. We're going to learn it as a weak acid equation. We're going to do one example of a base, and then once we set that, we're good. So with no further ado, let's go. So it's going to start with a mathematical foundation, and then I'm going to verify it with a visual observation from titration curves and come to a conclusion. But I want to give a preemptive piece of information here, and that is, if you've ever cleaned your room, I think you can probably agree with the statement. When you start cleaning it, it only gets worse. You're just basically consolidating mess, scattering mess. Entropy is clear when everything's messed around, and it looks horrible. But at some juncture, when you start cleaning up, you hit that transition point. You just feel it. Suddenly, you can see the first hint of clean and organized, and it gets better and better. That's what this is going to be. This derivation at about the halfway point will be one where you might want to just run and hide. I don't need it. Doesn't matter. And I hope you don't do that. I hope you work all the way through the derivation. But that's not the important part. Derivation is there just to show it's legitimately mathematically valid, but the application is what matters. So if you wish, and it's not jiving derivation wise, at least hang on and try the questions and discover how easy the equation is. But that said, I'm going to start with a simple icebox. I want to say I'm doing a couple things. So number one, normally you will see this as represented as H3O plus aqueous. And we do that because we want to keep track of all atoms. So when HA splits apart, a weak acid associates, the A minus is going to go off by itself as a conjugate base. H plus is going to glob onto water and form H3O plus. But because I'm using pH as negative log of H plus, I've decided instead of representing this as H3O plus, I'm going to represent it as just H plus. And they are synonymous. For all intent and purpose, they are synonymous. It's just really a personality choice. So there are some that actually will tell you even H0 plus is wrong, and they'll try to convince you it's H9O4 plus. I've seen that before, saying that it's actually four waters that hydrate together to solvate the H plus. I think that's where you're just splitting hairs. So note that H plus or H0 plus are both perfectly fine. I'm going to use H plus. The icebox, initial change equilibrium. So initially, I had some molarity, then just call M. Could be 1 molar, 0.1 molar, 0.3 molar, 7 molar, whatever it might be. I put this molarity in there. The water, there's so much of it as a solvent that I don't care, just an excess. There is no A minus formed yet because it hasn't associated. And I'm going to call this 0. So technically, it's actually 10 to the minus 7 molar, at least if it's at pH or a temperature of 25 degrees, it should be around there. Even temperature goes up or down slightly, it's essentially in that ballpark. But we're going to ignore it. That amount is so small compared to the molarity that it's irrelevant. So If we started with all reactant, no product, it has to shift in the forward direction to reach equilibrium, which means you must lose some HA, lose some water because it's an excess, I don't care. I'm going to gain H plus and gain an A minus. The stoichiometric ratio is 1 to 1 to 1 to 1. So if I lose X here, I'm going to gain X here and gain X here. So in the end, initial plus change equals the equilibrium quantity. Well, I have the HA, so M, the molarity is just now bracketed HA, the molarity of the HA minus X, whatever's lost, and then I get X and X. Okay, here's a caveat that holds true no matter what, whether it's Bennett equation or anything else, and that is the 5% rule. If that is less than 5% of HA, then we can ignore it. So mathematical thing, and the reason that is, let's just toss the numbers out here. Let's say that was 1.00 for HA, and I subtract 0.04. So 0.04 is 4% of 1, so it's less than 5%. So if I do that, I'm going to get 0.96, which if I round, will round up to 1.00. So anything that's less than 5%, in theory, will, if going to 2 sig figs, will create a number that when rounded is the same as what you started with. So it's our general rule. We're going to use it. For that to be true, the following must also be true then. That means the HA has to be large and the Ka has to be small. Meaning, HA is large, this number is big. If Ka is small, then only a little bit goes forward, so X is small. So HA must be much greater than Ka. We're going to say by 100 times. That's going to be our rule. So in order for the 5% rule to hold true, HA has to be at least 100 times Ka. So if I had 0.01 molar HA, that's 10 to the minus 2. And let's say the pK equals 5. That means Ka equals 10 to the minus 5th. Let's see if it would hold. Well, 10 to the minus 2 is 1,000 times 10 to the minus 5. So that would work. I can use it. Okay, so we have our stipulations. 5% rule says that the HA must be at least 100 times larger than the Ka in order to get a small x, a large HA, so that you can ignore the x. So equilibrium rules. Equilibrium constant, in this case we call it Ka because it's for an acid dissociation reaction, equals the products H plus and A minus, divided by the reactants HA and H2O, but because H2O is a pure liquid, we don't include it. So I'm going to go ahead and plug in X for the H plus, X for the A minus, but I'm only going to plug in HA and not HA minus X because I have no interest in a quadratic equation, and the X under these conditions is negligible. So we plug in and we multiply across, that'll be X squared. But note that X is H plus, so I'm going to do a little trickery here. And X plus, plugging in H plus for X, is just H plus squared. So if I were to multiply each side times HA at this point, so let's multiply this by HA, this by HA, those would cancel, and I'd be left with H plus squared equals the product of K times HA. Okay, I don't want H plus squared, I want H plus. So I'm going to need to take a square root of each side. So I'm going to find out that H plus, the square root of H plus squared is H plus, so the square root of this. Okay, we are now officially in the area of we're cleaning our room and it's getting worse. Because if you tell me this is an easy equation, I'm going to look at like you were insane. You can say that's nothing easy about that. You're telling me to take a square root of a product, not going to work. Guess what? It's just going to get worse because pH isn't H plus, pH is negative log of H plus. So if it's negative log H plus, I need to take this and substitute it in. And so this is the first key mathematical point. Okay, if you, I guess, revisits, if we flashbacks on what logs are, log is basically the exponent in a power over 10. So log of 10 to a power is just that power. So 10 to the third, log of 10 to the third is 3. So from this, we need some rules. Just like if you multiply numbers, you add their exponents. If you multiply numbers, you add their logs. So I'm going to say that this over here, this term right here, is negative log of the square root of Ka plus log of the square root of HA So that's within the bracket. So negatives outside, log of everything within. Remember that square root of Ka times square root of Ha, you multiply their numbers, which they're multiplied here, and you add their logs. Okay, so I'm going to get rid of this in a second, but note that this is the math I'm doing to get the following. Almost gone. Okay, oops, too much going on. Okay, so I did that, took negative log. Notice a couple things happen. The square root has gone away. Instead of the square root, I put a 1/2 power. So anything with 1/2 power equals the square root. So this is an exponent, and this is an exponent. And then I reintroduced the negative. So before, again, when I emphasize, I had negative of log of square root of Ka plus log of square root of Ha concentration. The square root became the 1/2. The negative got brought in here. And then this is the negative being brought in here as well. So it is working. I'm hoping you trust that this is valid math. It is. So I'm going to pull the 1/2 in front. So when you're dealing with logs, if you have like something to a power, that power can become a multiplier. So negative log of K to the 1/2 is just 1/2 log of Ka, and log of Ha to the 1/2 is just 1/2 log of Ha. Have to trust that this is log math that works, it's legitimate. So as I keep on going, I'm going to factor out the 1/2. I'm going to say 1/2 of this, 1/2 of this. So let's just add this to this. And I'm also going to make note that that right there is the pKa. Pretty cool. So 1/2 of the pKa minus 1/2 of log of Ha, put the 1/2s in front. And I'm going to start with that as the next thing, the starting point. Our room has gotten as messy as it's going to get. It's just going to get cleaner from this point. So I have this. Again, this is 1/2 pK minus log of this. Now, this value seems familiar to me. For whatever reason, I know that log of Hx, I think I did something with that. I can't remember what it is. So let's see. If Hx fully dissociates, then pH equals negative log of H plus, which we concluded before. And I'm going to clean this up. That just came out really bad on the screen. But because it fully dissociates, negative log of Hx. So that sounds familiar. So negative log of Hx is just the pH. And this is a log of Ha. So this is kind of the same thing. So this is like doing what we did for a strong acid. So I'm going to say we're going to do the same calculation that we do if this was strong. So you're going to see a little subscript pop up called if strong, and that's because of this relationship right here. So pH, I'm going to factor the 2 out, put it on bottom. pK minus log of Ha, and then 1/2 is a common term. So negative log of Ha, which again is the negative log of Ha is the pH if it were strong. Okay, this is it. No, there's no way this can be easy. Oh, it's a lot of stuff, which if you're still on board, and I hope you are, you're probably thinking, I think I know why it was only in 6 textbooks. Because at face value, this looks really, really hard, and that's probably why whoever's going through the derivation said, no, this Bennett equation isn't going to help me. It's not going to be useful for anything, and they didn't stick around to apply it. Okay, that said, I'm going to with a little caveat. There is a reasonable probability that if you go see a doctor, probably about a 20 to 35% chance that your physician, depending on where you're located, use the Bennett equation in their preparation for their MCAT. Just for what it's worth, it ends up coming around and being incredibly useful on a test where you have to go really fast and don't get a calculator. So it has its utility. So that's, I guess, ultimately where we're going. It's very useful for that. We're going to make it very useful for the class as well. Okay, I want to do a pictorial representation as well. So 2 titration curves on the same graph here. We have the strong acid. Notice it has no lip. It just starts out as it's logarithmic. It climbs ever so slightly, then suddenly shoots up to equivalence and then saturation or full base. The weak base has a lip. It levels off. It's a steady climb. So the buffer region, it isn't constant pH, but it's a slightly increasing pH. And so the 2 points you know on any curve, you know the pH at half equivalence for weak acid equals pKa, and you know the pH at the very beginning from just what we just did before, negative of the HX concentration. So it's easy to get that concentration and that concentration. Here's what is incredibly cool is this point is what we're looking for. That's what the pH we're solving for is, pH of weak acid. Ends up, that point is perfectly in the middle of the pK and the pH of strong. So the pH of a strong acid, the pK of the weak acid, that's right in the middle, meaning you take an average of this and this, which means add two together and divide by two, you'll get that point. So all that math, all that derivation, you're probably thinking, why did I waste my time? And I have zero answer for you when we could have just said, well, this graph says it is true. So we're on to some. Equation is set. This is the Bennett equation. pK plus pH if it were strong divided by 2 equals pH of that weak acid. And let's see how it works. So I have this. I want to make one note again. This only works if the HA is greater than 100 times the Ka. So note that this equation will break down if the HA is less than 100 times Ka. So just remember that. Okay, time to apply it. This part is where you will actually get empowered by it. So there's two things I need. I need the molarity and the pK. pK is given, it's nice and easy. Just double check. pK of a weak acid is anywhere between 0 and 14, so this is a weak acid. 10 to the minus 2, because I bounce it over 2, and then, sorry, 2 point whatever would be 2 molar. I'm gonna calculate down the road, but that's a 2 times 10 minus 2 for the molarity. This right here means this is something times 10 minus 5. It ends up it's 2. I'll put it in there as a placeholder, but even if you didn't know that, this is more than 100 times that. So Bennett equation can work. We're set. Weak acid, Bennett equation works, we're good. So here we go. Going to take the average, so we're going to end up with this equation, pH equals pK if strong. So first to figure out the pH if strong. So I need to figure out this is done before. So that means this is 2 times 10 minus 2. If you recall, the pH is simply the negative log of 10 minus 2 is just going to be 2. So negative power 10 will be negative log, so that's where that's going to go. And that's your mantissa. So we're going to get negative of a negative 2, going to power down, which is just 2, minus log of 2. Need to memorize some logs. Conveniently, because when you multiply numbers, you get logs. When you multiply numbers, you add their logs. I only need to get prime numbers. So those are the ones I need to know. Between 1 and 10, just remember log of 1 is 0, log of 10 is 1. So all these logs have to be somewhere between 0 and 1. So memorizing it seems hard, except life has made it easy for you. This 3 I'm going to bring over here. So I'm going to take that 3 and put it there. And in doing so, I'm going to make this 0.3 because it has to be between 0 and 1. So we're set. And then I'm going to take this 5 and bring it down here. So this is going to be 0.5. And take the 7 and bring it over here. Zero 0.7 and 0.84-ish. Okay, I bumped it by mistake, but that's how you're going to memorize it. So log of 2 is 0.3. So 2 minus log 2 is 2 minus 0.3, 1.7. So now the two numbers I need. I have my 1.7, my 4.7. So I'm going to just plug in. pK is 4.7, pH strong is 1.7. 4.7 plus 1.7 is 6.4. Divided by 2 is 3.2. Okay, first time we did it, this takes a little while. I'm okay with that. I'm going to get better. The more I do this, the better I get. But I only need two things solved for the pH. pK, which is a given unless they give me pK, and then I can easily convert. And then pH of strong is just a matter of put it in scientific notation and take negative to the power 10 minus log of the unit number based on what I memorized. If I do this, I'm going to get faster each time. So let's see if I can get a little bit faster on this one. So here are the important things. 3.3, I got that one. This is 1 times 10 to the minus 1. Bring it down, 1 minus log 1 equals 1. So 3.3 and 1 are the two numbers I need. So weak acid, check. 100 difference, check. So plugging in 3.3, check. 1, check. So 3.3 plus 1 is 4.3 divided by 2, 2.15. Pretty dang fast. Double checking with the other graph we had. Strong starts at 1. Weak starts with the pK 3.3. So only one number fits between 1 and 3.3, so could have done it pictorially as well. So these are ugly graphs, weak acid curve, strong acid curve. I drew them poorly, and I can still figure out what's going on. So it's got to be between the pK and the pH of it fully dissociated. So it doesn't fully dissociate, so it can't be as low as 1. It's not a buffer, so it can't be as high as 3.3. So 2.15 works. Pretty powerful. Let's do some more. Ugly number. This is where you say, this is roughly 0.1, slightly higher. So it's going to be 1 molar. So I'm going to say this would be 10 to the minus 1 because it bounces over. So 1 minus log of 1.0, time out, 1.073. Log of 1 is 0, so this is ever so slightly more than 0. So we're talking 0.9-ish, something like that. Okay, so between 0 and 14 is weak. I got my pK of 3.74. I got this number that equals 0.9897, 6, I don't know. I'm going to plug in one of those. Doesn't matter which one. 3.74 plus 0.97 is about 4.74 minus a little bit of whatever you decide this number is. So let's say around 4.71, 4.72. Divided by 2, 2.35, 2.36. Perfect, nice and easy. We'll do another one. This, I move this number over twice. So it's going to be 2 minus log 3. Log 3 is about 0.5, so it's around 1.5. Just going to take an average of these two numbers. 7.5 plus 1.5 is 9, divided by 2 is 4.5. Pretty dang fast. So bring your pK down, figure out what that is. And so as I've done a few of these, if you look back in the good old days of the derivation, it was a freaky thing. Didn't know what to do with it. I realized I don't need derivation ever again. I just need to trust this relationship. Derivation was simply to support that that's a viable equation. It is a viable equation, so I'm just going to plug in 7.5 plus 1.5-ish. 9 divided by 2 is 4.5-ish. If the answer is 4.51, you're right in the ballpark. That's all that matters. Okay, so what if it's a base? Same thing you should be asking yourself with any equation you run into in acid-base chemistry. So again, I'm going to reiterate that, let's say this is something totally different. Off on a tangent. Sorry, the writing program is not working out as much as I would want it to. That's a Henderson-Hasselbalch equation. For the basic form, you can just simply change the pOH, pKb. Better. Plus log of HA or A minus. Acid form, base form. So what do we do with the Bennett equation to make it a base? We simply return or replace all the pKs with pKbs, all the pH with pOHs, and we're set. So pOH this time instead of pH equals pKb instead of pK plus pOH if strong. And we do the same thing we did before. We take our pKb and we plug it in. We take our thing and we say it only moves over once, so it's 1 minus log of, that's roughly 3. Log 3 is roughly 0.5, so I'm going to put in equal to a 0.5 right about here. So 9.6 or 9.26 plus 0.5 is 9.76, around 9.8-ish. Cut it in half, it's around 4.9. So we'll come up with 4.89. Can actually do this fast and in your head. So there's really only 2 calculations, and they're both relatively simple. Move the dot over until you get to the place it needs to be for cycling notation. Moves over once, 1 minus log of whatever that whole thing rounds to, 3. So 1 minus log 3, that's one calculation. And then that number you got plus the pK divided by 2, you're set. So it's time to race AI. Oh, it's not time to race AI. I just realized this question asked for pH. My mistake. So pH is pH plus pOH equals 14. So pH will be 14 minus pOH. So plugging in 14 minus 4.89, well, minus 5-ish, so 9 point something. Is it 911? Nice. This is actually working out well for me. Time to race AI. So you need 3 players to do this if you want to. I'm going to play person 1. I'm going to put the numbers in and want you to either use AI or to do the Bennett equation. I'm going to use the Bennett equation in each case, but I will say I've tested this on Gemini and a few others, and it ends up when you punch it in, it takes on average, depending on the AI, about 14 seconds from the time I first start typing it in to when I get an answer out. So the question is, can the Bennett equation be faster than 14 seconds once you have it mastered? Let's find out. So this is something I'm going to hopefully have everybody try. You have a situation where person assigns a pK and molarity that fits the constraints that this works for. One person is plugging the AI, they're going to get it back in 14 seconds and confirm, yep, 14 seconds, got it. And the third person is going to plug it into the Bennett equation. So let's go ahead and set up the Bennett equation. So it's going to be, what is the pH of some molarity of acid, HA, and then pKa equals something. And if it's a base, it'll be pH of the base, and I'll have a pKb, whatever I have. But let's just start with the simplest case. So here's the Bennett equation again. You take an average of the pKa plus the pH if it were strong divided by 2. So if you're ready, you're going to click on this. And if you want to try AI first, so you get, and then try the Bennett equation second, see if you can do it as fast. At first, you may not be able to, but I guarantee if you do 3, 4, 5 of these, you'll become faster than AI. So let's see how this works. The pH is strong is going to equal the following. Moves over 1, 2, 3. So 3 minus log of 5 is 0.7. So there's my chart. 3 minus 2.3. 4.86 plus 2.3 equals 6. Round up, 7.16. 7 over 2 is 3.5. Half of 16 is 8, so 3.58. Done. I've done this thing before. I mean, you can throw me whatever, and because I'm familiar with it, I'm going to be fast enough. The goal isn't for me to say I'm fast. The goal is for you to get to that point, figure out what it is. So bounce a dot for the first part of the pH of strong, memorize what the 5 is, or the 3 is, or 2 is. If we're 4, log of 4 is 0.3 plus 0.3 or 0.6. Log of 6, 6 is 3 times 2, so it'd be 0.77 or 0.778. So about 8-ish or so. So you have like ways to get the other numbers, but there's this number you have to get right here from bouncing it over. This number you have to get from memorizing logs. Then you have to do a little bit of math to say that equals 2.3. Put it in there, put that in there, average it, and you got your answer. So I'm going to try one more race the AI. So if you're ready, on your mark, get set, math on. You got to bounce it over twice. So 2 minus log 2. Log 2 is roughly 0.3-ish. This is slightly higher, so I'm going to make it a little bit higher. 2 minus 0.32 is 1.68. 5.52 plus 1.68 going to work out fairly nicely for me is 7.2 divided by 2, 3.6, 8 seconds. AI still has 6 seconds to go. You can be faster than AI if you master the Bennett equation. So we're calculating the pH. Again, if you have a calculator, you're just going to plug it in. That's fine. If you want to do the work all the way, that's fine. To show all your work, that's good. If you're on a standardized test, you get no partial credit for showing your work, and you have to go fast, and you get no calculator on most standardized tests for health sciences. For other ones, you might get one like GRE, but for health science ones, you're highly unlikely to get a calculator pending the exam. So this method, really, really powerful. Hopefully it works out. Hopefully you sit there and go, this is the greatest thing ever. I don't think you'll say that, but again, incredibly useful because it's such a targeted thing. You'll probably find it standardized test materials now, but the Bennett equation, fairly useful. Hopefully you learned it. And if you're in my class, my actual class, you will, if you use this, you'll blow through the test and you'll have plenty of time to just relax and still get a good grade. Thank you for playing along, and I will see you at the next Toddcast, at a Toddcast in class, or somewhere along the path of life. Thank you. Bye.